The idea of a U substitution as a technique comes into play because there's no such thing as the anti-product rule, and there's no such thing as the anti-quotient rule. So anytime you have a product or a quotient that's part of a multiplication, U substitution is going to be the way to go. So U substitution, again, there is no such thing as the anti-product rule. It happens all the time that people just try to simply take the antiderivative of each part and multiply them together. That's not how antiderivatives work, because it's not how derivatives work. Same thing for a quotient rule. They look at the numerator and the denominator and they just try and do the antiderivative of each, but not the case. So last year you guys learned how to identify what a good U was. We're going to not spend I'm going to assume for the most part we're going to be pretty quick at identifying a good U substitution. So here you go. Here's your first example. This is a product between an x squared, a parabola, and an exponential. The U that you choose, most often you'll be able to recognize the relationship between a derivative and antiderivative. The one that has the higher power is what you're going to choose for your U. So in this case, the x cubed is what we're going to choose as a U. And it's going to end up taking care of that x squared that's next to it because it has a lower degree. So in U substitution, you'll want to identify that x cubed is what you're choosing as your U. And then you're going to find the derivative on both sides. So the derivative of x cubed is 3x squared, and the derivative of U is du dx. Then we work to get dx by itself. So if 3x squared is equal to du dx, that leads to dx by itself being equal to du over 3x squared. So one leads to the other. When you use an arrow in math, that's meaning like from one I can get the other, that it implies the other or leads to the other. So when you come back to your integral now, you can say this is equal to the integral of, okay, leave that x squared alone, but trust that it's going to get taken care of. And then multiplied by e to the u, because we're replacing x cubed with u. And then at the end, we replace dx with the equivalent expression du over 3x squared. And then you can see, look at the x squareds get eliminated from this integral. So we can reduce away our x squared. And we're left with the constant 3 in the denominator, which means I can pull a 1/3 out of the integral. Once we've pulled a 1/3 out of the integral, then we can work on finding the antiderivative. And the antiderivative of e to the u is e to the u divided by Lenny and divided by 1. So 1/3 in front of e to the u over the natural log, which simplifies to be 1/3 of e to the, and at the end you change the u back to what you had chosen u to represent, and u was x cubed in the first place, and then plus c. Do you remember how to check your work? How do you make sure? Take the derivative again, right? And by taking the derivative again, I should end up back with the original product that I started with. So if you're ever wanting on a quiz or test to double check and you have time, retake the derivative and see what you get. All right, here's another one. This is a sample again of a multiplication. So we want to say, okay, what would we choose as our u? You may want to think of this as parentheses, 1 plus x squared quantity to the half dx before you identify your u. So Casey, what would you pick as your u in this situation? So what part of it? Yeah, usually the thing that's in the parentheses, especially if it has a higher power than what's outside of the parentheses, the thing in the parentheses is going to be good to choose. So choosing 1 plus x squared would be for our u. The derivative of that is 2x equals du dx, which implies then that dx by itself is du divided by 2x. So once you've identified your u and your differential, you can go back and substitute. So the parentheses become u to the half. Remember, the 6x doesn't change yet. It's just 6x and then u to the half. And then du over 2x, substituting for dx. So that we get this taken care of by reducing again. So we reduce the x's and the value of 6 into 2. So we have 3 outside of the integral of half u to the half du. So then you're home free. You're in the home stretch. So my antiderivative will be 3 u to the 3 halves. So we're raising the power. And then dividing by the power of 3 halves. Or it's cleaner to multiply by the reciprocal. So multiply by 2/3 instead, plus c. And then you reduce that and come up with your final answer. So my final answer is going to have a coefficient of 2. And then my u is going to be 1 plus x squared, put back with the new power of 3 over 2, plus the generic constant of integration. Yeah?
How come we don't need to do brackets when we anti?
Yeah, I should be doing good brackets. Since it didn't have bounds, I was getting a little sloppy. Yeah.
They only, like, the FRQ section won't take off for brackets.
Not if you don't have bounds. Right, if you have bounds, then for sure you want the brackets on there. All right, so here's one that's a quotient this time. And almost every single time in a quotient, it's the denominator that will be your u. So you're going to choose your denominator first. And this time, what else is different? Besides it being a quotient, what else did I give you that's different? There are bounds. So first we identify that x squared plus 9 is going to be our u. So the derivative would be 2x equals du dx, which is going to imply then that dx is du over 2x. With bounds, you have a choice. I usually convert my bounds. And then I never have to go back to, so you have to convert at some point. Either you convert your bounds now, and then you're in the home stretch, you don't have to ever go back to any other variable, or you don't convert your bounds now, but you have to remember to change u back to x, and then work with the original bounds. It's less work to change your bounds at the beginning because it makes the math easier, but it's not wrong if you forget to change your bounds as long as you remember to change the u back to the x term. So I usually change my bounds. And so you change your bounds by u. 0 is going to convert to -9. I get that because I just plug 0 in for x in the x squared minus 9 expression. And 2 is going to convert to -5. And again, I get that by plugging 2 into x in the original expression. This is what I usually do because I find the math turns out easier. So then I'm ready. My new bounds are -9 to -5. x is my numerator while u is my denominator. And then du over 2x is my differential. So as I reduce and simplify, I'll be pulling half out of the integral, and I'll be left with 1 over u du. So this format of 1 over u du is the only time I would use natural log. I'm not going to do it for 1 over u squared. I'm only going to do it for 1 over u. So this would be half, and now bracket, Giselle, natural log absolute value u plus c. And my bounds go from -9 to -5. Now the absolute values end up being important because when I'm putting in -5, it's going to convert that to a +5. So I'll have half of the natural log of 5, positive, minus the natural log of 9. Which can be simplified to half of the natural log of the fraction 5 over 9. So remember, this represents the amount of area bounded under the original curve between 0 and 2. So it'll be the irrational number 1/2 ln 5 over 9. You will get the exact same thing if you had decided to change this back. So if you had done the natural log and then change back to x squared minus 9 plus c and used the original bounds. So if you changed it back to x squared minus 9 and went back to the original bounds, you're going to end up with the exact same thing. You'll still end up with the natural log of absolute value of -5 minus the natural log of the absolute value of -9. So you get the same thing either way. All right, I only have one more example. Can you hang with me on one more? This is back to another product. Here, this is an example of where you don't choose the higher power as your u. So a lot of times you do choose the higher power, but this is a time where you don't choose the higher power because you should recognize that tan and secant squared are related to each other. And so you want to choose the one that's not the derivative for your u. So just because secant squared has the higher power, don't pick it. Because think about, all right, if I choose secant squared as my derivative, I have to do the derivative of that, which is not going to be very clean with a tan. So we want to choose tan because the derivative of tan is secant squared. So we'll pick tan x as our u. The derivative of that is going to be secant squared of x being equal to du dx. And then that will lead us to dx being alone, which is du over secant squared. So you should be able to kind of preview, like look into the future and see, okay, I'm looking into the future and I know that choosing this u is going to result in a secant squared, helping me reduce. I also want to, I'm going to take the time to convert my bounds. So 0 is going to convert to, so I'll take 0, I'll plug it in for x in the original u substitution, and that still gives me 0 since the tangent of 0 is 0. But pi fourths, if I plug that into the x position, what will that give me as a new upper bound? 1. Good. So this will become the integral from 0 to 1. U takes the place of tan x. Secant squared is still part of the product, but the du substitution is going to take care of that secant squared for me. So reducing works out pretty clean. If you're not reducing and getting something more simple than what you started with, you're not doing it right. Something's wrong with the U substitution choice. So I just have the pretty easy integral of 0 to 1 of u du. Guy, you can do this with geometry because this is just going to be a triangle under the line u, but you can do it with antiderivative also. So that would be 1/2 u squared plus c going from 0 to 1. And I don't ever have to go back to tangent. If I do go back to tangent, I'd have to go back to the original balance. So I don't want to do that. That's extra work. I'm just going to stick here. And so I end up with 1/2 times 1 squared minus 1/2 times 0 squared, or just 1/2. And so the amount of area between 0 and pi/4 under this product of tan and secant squared works out to be just equal to 1/2. So it's a rational number.